Okay, I'm Jerry Dowling, and I'm the speaker today. And we'll be talking about sensor performance, backgrounds, and contamination. And the bad guy in this story is, of course, contamination. But it'll take us a little while to get that. About 20 years ago, the illustrious director of the Space Physics Laboratory, Robert A. Becker by name, decided the people in far-infrared spectroscopy were having too much fun, and on top of that, we needed to become relevant. So Doug Rawcliffe, who was in our group, moved off into his favorite satellite program. Dick Hall chased off to Florida to measure transmission of clouds. Charles Randall was eaten by some computer, but got regurgitated because it was indigestible. And I found myself joining the so-called infrared military community. And Bob Becker told me, he said, "You'll love it there. These guys don't know what they're doing. They don't know where they're going." And to that extent, I gave a talk, about 7 years ago. And there were some improvements in the infrared community, but many of the problems and questions still remain. It's good 7 years ago. It'll probably be good 7 years from now. Why backgrounds? Well, at that time, the military community was interested in a concept called surveillance, and they still are. And the reason being that even if everybody's your friend, you still want to know what they're doing, and instead of calling it spying, you call it maintaining a surveillance posture. And this is exactly the sort of problem they wanted to solve. The assets on both sides were increasing, namely the space assets on both sides were increasing, and it had to be figured out, to figure out some way of keeping track of it. So a surveillance type study was awarded many, many years ago, and it culminated in a so-called Phase 0 contract, which was titled High Star BMS. And of course, these things always had to go through Washington and various and other sundry places, so you needed a real spectacular view graph to why one wanted to do this sort of thing, and here it is. It has been upgraded from time to time, especially the center thing here. This last upgrade, or the last upgrade that I have, has the shuttle with a sensor peeking out. In fact, it's the SIRE sensor, so that makes it about 10 years old, maybe 7 or 8 or 10 years old. And you can see there's something for everybody. If you want to see what's going on or what everybody's doing, you could ideally fly very, very high and look down. But things like ranges get to be very large, and therefore your sensitivities become a little hard to maintain. Or you could fly so low that you look up and see everything that's going on. Unfortunately, if you fly that low, you don't last very long because you get dragged down into the atmosphere. So you got to figure out some intermediate region, and that, of course, is what was done. And it came to the conclusion, hey, if we're going to have a surveillance type system, we better know what kind of backgrounds are we going to be looking into. For instance, when you're looking up, you got hot and cool stars, you got galactic dust, namely zodiacal light, you got all sorts of interesting things, and even some things flying up there. These are backgrounds that you have to contend with. And of course, things like stars present point sources to the sensor, and so will so-called interesting objects. So you got to have some way of distinguishing between the two. And in the wavelength region that of interest, which roughly runs from about 6 to 25 microns, a so-called passive band in the infrared, anything that is at a temperature will always radiate in this band in one way, shape, or form. So you can do it passively. You don't have to have a radar type. And of course, things will be flying underneath you too that you'll want to see. And therefore, you'll have to look down, and here things get really interesting. You have things like the Earth limb. You have red arcs, have noctilucent clouds. And if you look far enough out, you might even see galactic dust again. The Earth itself is a beautiful sort of thing. You got nighttime, you got daytime, you got the Terminator, you got auroras, all sorts of interesting things. There's something there for everybody. In fact, it was right about the time that they were doing, or this view graph first came out, that I got on the program, and I think the program was supporting about 5% of the known astronomers at that time, okay? And some astrophysicists, because, boy, look up, and for cool stars, that was a big thing in those days. And, of course, we also got atmospheric-type people, knock the loosened clouds, the Earth limb. Look what's happening when you go across the Terminator. And for science fiction fans, there's even a thing called Markov layers. I'll discuss that later if you want to know about it, but you really don't. Okay. The backgrounds are important because you have to operate against them. In fact, you want to be able to operate as close to the Earth as possible, because in operating close to the Earth as possible, you get the greatest volume of coverage for your particular sensor. And one of the things that you have to worry about is the emission of the Earth limb. Now, nitrogen and oxygen don't present much problem, but things like water vapor, ozone, nitrous oxides, and various other sundry things, carbon dioxide, of course, present big problems. This is a really ancient view graph. Yeah, I've got it from a couple of my friends at the geophysical labs, and it still has the title Air Force Cambridge Research Laboratories. That's really old. And essentially what it is a estimate of what you would see if you had infrared eyeballs and looked, or standing above the Earth and looked down at the Earth at 100 kilometers tangent height, between 2 and 26 microns. This big thing in the center here is the well-known CO2 emission. There is another one over here at about 10.6. This bigger one, I think, is ozone. You got water vapor here and a few other interesting things here. Get back to the practical sort of thing. The Air Force wants to know, hey, where can we look the furthest? You can look the furthest where the backgrounds are the smallest. So you're interested in the window regions. There's a window region right here between about 11 and 12.5 microns, another one sort of in here, one over here. This is really, even at that time, not even at that time it was a sophisticated form of guessology. Really didn't know, wanted to make measurements. In comparison, if you look directly at the Earth, you would see a black body, or a quasi-black body, at about 290 degrees Kelvin. And on this graph, 290 degrees Kelvin would correspond to somewhere between 10 to the minus 4th and 10 to the minus 3 watts per square centimeter per steradian per micron. Okay, so the people said, hey, we want to really know what's going on down here in this region here. And we've got a thing called the Earth radiating this much up here. Keep it out of the field of view, of course, but can it hurt us? So the idea of non-rejected Earthshine, or reject the Earthshine, came about, and the following simple-minded argument was made. We got 10 to the minus 3 up here, and we really would like to get down to 10 to the minus 13th. We need a rejection ratio of about 10 to the minus 10th. 100 kilometers tangent height for the satellites that we want to fly will be looking about 1 or 2 degrees off the Earth. So this was the name of the game in the Phase Zero contract. The contractors were told to design a sensor that could operate against the Earth so they could make measurements in the 10 to the minus 13th domain without being contaminated by that big red Earth. And this is the stage of the game that I got on the program. Part and parcel of the statement of work included a statement to the following. The contractor shall deliver approximately 1/2 scale models of their sensor for off-axis rejection testing by an independent agency. Space Physics became the independent agency, and I became the independent agent. Went to a number of meetings, tried to find out what these people really had in mind. They had in mind, of course, the thing that I sort of tried to describe here. How well will a given sensor design or a given sensor model operate against a radiating Earth so that it can make measurements way deep down in those windows? And in order to make sense out of this sort of thing, I had to invent or reinvent the quantity called the point source rejection function. And it is the following. Consider a radiation source which is a point source located at infinity. Namely, it's a collimated beam. You let this collimated beam fall upon the sensor aperture and you line it up on axis. You get a reading off the detector, full blast. That is the so-called I0 reading. You then take the sensor and tilt it about its entrance aperture, an angle beta. You get another reading Call that I beta. The ratio of the two is a so-called point source rejection function. If you have this function, and it may be a function of more than just one angle. If you have an asymmetric sensor, it will be a function of two. If you have this function, you can use it to find out the performance of the sensor against any sort of extended body. Okay, the job was relatively straightforward then, at least in principle. All I needed was a collimated beam and a rather powerful source, and came up with the following concept. Let's look at the side view first. A is a CO2 laser. B is a chopper. C and D are iris diaphragms. E is a secondary mirror, which expands the beam out onto an off-axis paraboloid, which renders the beam parallel. That gives you the parallel beam, the point source of infinity. Then over on a clean bench, you have mounted on an optical or a rotary table the sensor you want to investigate, and you move your source around, making measurements as a function of beta. Two things here. The logical thing to do originally would have been rotate the sensor, not this big bloody thing here. However, there were two reasons for not doing so, one of which is not terribly important, but practically it was. The other which is really terribly important. The not so terribly important but practical one was the sensor contractors did not have to decide on the design of their sensor until literally 2 weeks before the due date. And one of them threatened me with a 15-foot shield hanging on their half-degree sensor. So I would have had something like 15 feet hanging out here with the sensor out here, and have to move that around would be rather difficult. The threat never came about because, as it turns out, that would have been the design that they were stuck with if they won the contract. The other thing is that the sensors had to be kept clean, and therefore it was located. We had to locate them in a clean table or clean bench type area, and that was done. Now, this was in about 1970, 71, and I really have to say, at this time, I had been working at aerospace about 6 or 7 years. I really felt that aerospace had a first-class research organization. From the following point of view, we scrounged everything, with one exception. Scrounged everything. Well, there were some things that had to be built in the shop, like the movable bench, but just to give you an idea, this is what it looked like. Now, it doesn't show very well, but here's an 18-inch off-axis parabola, which we just happen to have laying around. It was the fraction limited at 5 microns, but we worked at 10 microns, so we really didn't care. Here is a CO2 homemade laser from, what is his name? Well, he's a real nice guy. He lent it to us because he was ordered to, but more important, he lent us the technician to run it. Otherwise, we would have killed ourselves. There's no two ways about that. Here's the power supply. Here's one of the diaphragms. And over here is the clean bench. And over there is mounted a sensor. But the sensor contractors felt that their designs were proprietary and therefore no pictures. In fact, one of them felt his sensor was classified, and it had a first-class seat from Massachusetts. Out to here. No, I'm sorry, Connecticut. Out to here. And they put it all together. We measured it, and then they took it all apart. Now, the one thing that we couldn't get done in-house or buy easily was the secondary mirror. It had to have a relatively steep radius of curvature because it had to expand the beam out to get onto the mirror here. And that's it, right there. And since it was the only thing that wasn't scrounged, it was the only thing that I could keep. Sort of like a trophy. What is that thing? It's a ball bearing. They came in packages of 3, but you had to buy 6. We ruined one mounting it, but the other one got on, and the other 4 disappeared. One wag in my group said that the Jolly Green Giant came and got it because he was going to play Captain Queeg in the King Mutiny, and he needed it. And as you can see, time has taken a little toll on it. It has become quite a bit corroded or contaminated, but it was really very good. Ball bearings, in essence, are very smooth, and We had no difficulty using this thing. And in fact, since it has cylindrical symmetry in this direction, we didn't have to provide for any adjustments in that direction, only back and forth and up and down. And as you can see, we had some magnificent up and down motion there. Okay. This thing had two problem areas. After the source selection committee met and the winner was decided, they decided I could keep the model sensor for a while and play around with it to see if I could improve the measurements. And it turned out that I really couldn't, and because there are two things playing against you. If you have a sensor sitting over here and you take this mirror and rotate it around, when you're in very close to the zero position, the sensor detector can see the mirror. It actually can see the mirror. And in fact, what you might be measuring, unless you have a very small field of view detector or a very good mirror, you might be measuring scatter from the collimating mirror rather than the point source rejection function of the sensor. To beat that, what you do is say, okay, I just have to take this mirror and move it way back someplace. Give this a real long throw distance. And this was a big room. And so I tried doing that to a certain extent and didn't improve the data points very much. A little bit it did, but kept getting into another problem. And the problem, I believe, and I believe it is true, is that we were in a dusty room. And you move the mirror back, there's more and more volume that the sensor can see that's illuminated by the laser, okay? And a dust particle comes floating through there, and forward scattering is very, very good, right down the sensor throat, and you got a background that, again, jeopardizes your measurement capability. Okay, two side items. I got into big trouble in this program at this time. The contract says, hey, you got 2 weeks before a given date to deliver the sensor, and it turned out 4 weeks later the source selection committee met. And I had to have the data done and analyzed by that time. And one sensor contractor was late, so I called him up and told him to get off his butt and get his sensor down here. That was a bad, wrong thing to do. Sensor contractor construed that as direction. And direction has a particular meaning contractually, i.e. they were able to ask for more money. So I got into trouble with everybody. I got into trouble with Bob Becker, my boss. I got in trouble with the program office people. I got in trouble with the Air Force. And for at least the next 3 years, I could not speak to a contractor without somebody holding my hand. The other thing is that at that time, they had a thing, or they had a sort of paperwork thing called a U-44. Now, a U-44, we describe it in very few words, is how ION Aerospace saved the Air Force tons of money, brought them lots of prestige, saved them gallons and gallons of time, in other words, saved their backside. Now, writing these things up is easy. There are no two ways about it. The real difficult thing is it does not become a legitimate U-44 unless you get the Air Force program officer to sign it. Here it is. I found it this morning, and I'm so happy. I've been in the aerospace for quite a long time, and I consider this one of my prime accomplishments, achievements. Get back to the problem that we have with this setup. You don't want to be too close to the primary mirror or the collimating mirror because you'll be measuring its scatter rather than the OFVR of the sensor. You don't want to be too far away either because you got dust falling down. Well, you can get away from the dust easy. Just work in a vacuum. Okay? If you work in a vacuum, you can go way back and get a very small throw distance and solve everything. And now comes the biggest scrounge in the world. The Air Force would not build us a situation like this, but they did happen to have one. This is in Tullahoma, Tennessee. I'll say a few words about Tullahoma, Tennessee later. This was a tank called the Mark I chamber, and essentially it was used for testing of rockets. And the name of the game is what they're really interested in, the performance or how rockets behaved at high altitudes, not down on the ground. So they built this great big tank that they could pump down. They'd put a rocket right in the middle and shoot it off, and they'd get about maybe 10, 15, 20 seconds worth of data that was good, depending upon how big the rocket was. But they quickly found out that, hey, they could really sort of double or triple their time if they cooled all the walls to 77 degrees Kelvin. So this was a quasi-cryogenic tank. It's just what we wanted. And in fact, you can see the design here. Sitting up here about midway is the laser station. It goes out to a secondary mirror, which floods a collimating mirror on the floor, which goes up to a sensor sitting here. And they built it. Okay. Oh, yeah. Tullahoma, Tennessee. If you know where Nashville's at, and you know where Chattanooga's at, and you know where Huntsville is at, draw that triangle, okay? Then sort of put your finger right in the middle, and that's Tullahoma, Tennessee. And believe me, nothing happens there. The first time I went there, I was told that it does have one saving grace. The city of Tullahoma is nothing. The larger town is Manchester. But it's in Coffee County, Tennessee. And for those of you who are sipping bourbon type people, you know that's the home of Jack Daniel's Tennessee whiskey. That's the good news. The bad news is that it's bone dry. So that, yeah, they did have tours through the Jack Daniel's distillery, but you got no free samples because it was against the law. You got a shot glass, empty. Okay, the number of sensors were measured here, in fact, quite a few, and the results were really quite interesting, but I don't want to show you the data right now. I'd rather show you one of the sensors that was measured there early on. And this was from the BMS program. It's the Earth limb sensor. And as you can see, this is another Washington, D.C. type view graph. And it was really a very nice sensor. It was an off-axis paraboloid. Here's the off-axis paraboloid. It caught the radiation coming in down through what they call an off-axis rejection stop, and it was really nothing but a field stop, onto a first relay mirror, through a Leo stop. Leo stop helps suppress diffraction, over to another folding mirror, into this maze here, which is a lot of spectroscopy being done, so that they could look at things like emission bands, windows, edges, and so on and so forth at various tangent heights, hopefully under various conditions, so that they could determine, hey, how good is a window, how wide is it, how long does it stay that wide, and so on and so forth, and all sorts of things. In fact, the BMS stands for Background Mapping Satellite, and this was the Earth limb sensor. It was supposed to be up for about a year, year and a half, and under that time period, you should have been able to see a lot of things. It was later downgraded to another program called ELMS, and then finally that was canceled, but this sensor did fly. It flew as ELS on a geophysics lab probe. We'll be back to this just a little bit later on. Okay. What causes the problems in out-of-field of view rejection? In other words, what makes the point source rejection function different from zero? Well, let's take a small, simple sensor like this. Here's a primary mirror, and about it we put a telescope barrel. Don't worry where the focal plane is or things like that. This is good enough. Let an electromagnetic wave come in, and of course, things that are perpendicular to electromagnetic waves are called rays. So we'll take this first ray. This first ray intercepts this edge, say, and the light gets diffracted. And it can get diffracted into the field of view of the sensor and find its way back to the focal plane, and therefore you've got one source. Here's another portion of the wavefront, 2, this ray. It just goes all the way through and hits the primary mirror itself. And of course, if there were nothing else happening, it would form an image of the Earth someplace in the system, which we would block, and we have nothing to worry about. But of course, the mirror scatters, and it will scatter radiation into the field of view, another source. And then finally, we have this 3 here. It hits the side of the telescope barrel, splashes it around a little bit, and then hits the primary mirror, part of it, and gets scattered. So this is a sort of a second-order effect. So the 3 main contributors, at least as far as I'm concerned, are diffraction, primary mirror scatter, and second-order things. Okay, here is some sort of quasi-data. Now, I was going to show some real data, but it's still, my copies are still not cleared. I ginned this up for a problem that I wanted to discuss with some people at a meeting. It's for what I call a model sensor. This is the point source rejection function. As you can see, it's defined to be equal to 1 at 0 degrees. So you'd have to get up there in Hugh Ruge's office someplace to get to the 1 point. Right around at very, very small angles, of course, you have the image itself. And then it falls off due to diffraction, also due to aberrations and things like that. But then as you get further and further out, it comes sweeping down. And in fact, this portion of the curve is about a 1 over beta cubed behavior. And that's sort of what you expect for diffraction for circular apertures. Sooner or later, though, what catches on, though, is something that goes just a little bit slower. And this is due to the scatter off the primary mirror. And it usually happens at relatively small angles. Now, the telescope itself, of course, will have a barrel, and the length of the barrel the diameter of the mirror divided by the length of the barrel gives you the maximum angle at which an out-of-field of view source can illuminate the mirror. And therefore, beyond that, you don't see anything more. And you can see the L over D ratio for this sensor corresponds to about 17 degrees. And this stuff over here is a second-order effect. This is what the formula looks like. A is a constant, depending upon what your aperture is. Beta cubed is obviously then a circular or a concentric circle type thing. For rectangles and squares would be slightly different. So this is the diffraction term. This is the mirror scatter term. B has things to do with the mirror scatter characteristics, detector field of view. And this is sort of a measured parameter. You have to know how the scattered light dies as a function of angle. This is the so-called shadowing function, and it asks essentially how much of the mirror is illuminated for a given angle beta. And of course, when that angle gets to where it equals the D to L ratio, f of beta becomes 1, and this drops out, and you have no more contribution from the mirror. And then finally, here's the second order term, and this turned out to be an empirical sort of thing as far as I was concerned. Actually, this is a very unsophisticated way to look at a sensor. On the other hand, it really is pretty neat if you're in the design stage. Somebody from the program office comes over and says, hey, we got these 10 designs we want you to look at. Which is the best with respect to out-of-field of view rejection, or which ones show promise? In that case, this sort of thing does a very good job. Usually does a very good job. When you get down to the nitty-gritty of it all, though, then you have to become more sophisticated for two reasons. It's a little hard to write down the diffraction things. You should really be throwing in BRDFs of everything, not just the mirrors. And the second-order effects, as I said, are empirical. You should model them some way. There exist computer programs called APART, Arizona Periaxial Ray Treatment. Okay. Then there's GURAP. Okay. All these things exist, and believe me, we have people at Aerospace that do that sort of thing for a living. Yvonne Kellogg is one of them. And when you get beyond the stage where it becomes more important that you know what's going on, and also you want to know that you haven't made any stupid blunders, then a thing like GURAP or APART is extremely important. So you got your commercial. Okay, I want to talk about each one of those terms, and I'll start with the one that I thought was the least important, and namely the second order terms. And that has to do with baffling in the telescope barrel. Why do you put vanes in the telescope barrel to baffle it? Well, suppose you have an incoming I0 beam of energy, and it just sort of grazes the telescope barrel, and if the telescope barrel wasn't there when it kept on going, you wouldn't have to worry about it at all. But because it is there, it reflects off. And at grazing incidents, especially in the infrared, damn near everything is a good reflector, like a mirror. So you really don't get much attenuation here. And boy, if that's off and racing towards the mirror, you've had it. So what do you do? Well, you put a vane in like this, so when the beam comes in, it bounces, and if you're real lucky, it bounces out. If you want to play other kinds of games, maybe you want to tip it a little bit, so you make it bounce many, many times at rather small angles, so you get a lot of attenuation. There is reasons for considering one over the other. For instance, in the type of sensors in the infrared that I have been used to dealing with, heat load is an extremely important quantity. You've got to cool the whole telescope, including the telescope barrel, if you want to maintain performance. And if you can throw a photon out rather than absorbing it, so much better for you. So the rebounce out sometimes is to be favored over the catch it in the corner. And now, as I said, I didn't think I would really have to worry about talking about this much more, but there is an interesting problem that arose in November 3rd, 1988. I walked into my office, and this was one page of a 13-page fax sitting on my desk. What it is it's the low light level TV camera for the IBSS program. Infrared background survey signatures, right. The other 12 pages were almost incomprehensible, except for a note from Norm Keegan that said, Ray Russell will be calling you about this pretty soon. And the explanation is right here. This is worst. Rejection ratio estimated to be 10 to the minus 4th to 10 to the minus 5th at 45 degrees off axis, gets worse at less than 45 degrees axis. And that's not good enough. In fact, it's far from good enough. So Ray finally did get a hold of me, and I told him, I said, it'll take me about 2, 3 weeks, maybe a month to go over the things that these people had sent with respect to how their baffle system works. And I got back the statement to the effect was, we don't care what went wrong. Can you fix it? So I got to design it. And when one looks at it, and I'm not going to give you the magic that I went through, one can redesign it. And here's the redesign that I came up with. Now, essentially, all the black, this line here, 6 down here and here, that's the can for the baffle. That's sort of fixed. It defines the aperture that goes back to the TV camera. It also defines the field of view. So you really can't do too much about that. Only this, and this were at my disposal. Well, you can see a number of things are different than on the first design. First of all, there are fewer baffles. 1, 2, 3, 4, I believe there were 8 on the other. The other is that they're not equally spaced. I don't know why they had them equally spaced. I don't know why they had 8. But definitely, baffle designs that have to put up with this sort of thing, more is not better. And then the third thing that had to be specified, and I don't think was, is that these edges should be extremely sharp. And I think Ray asked me, what does extremely sharp mean? And I said, what you do is get yourself somebody that's not too brilliant and have him put his finger on the inside and feel the edge. If it doesn't come out bloody, it's not sharp enough. Okay, so I mean, they're as sharp, it means you should make it as sharp as possible. Well, the rest of this war story is not all that interesting. Got communications from AFGL and a few other places which I didn't sort of understand. However, to give you some idea that it was appreciated by an outside source, here's a letter of appreciation that came from the IBSS systems engineer. And this is the critical thing. IBSS L-Cube TV has now been tested and delivered. We have seen a dramatic improvement of several orders of magnitude. The instrument is now usable. That's a nice thing to have. Get it put in your file folder, too. Bloody? Okay, well. He didn't tell me that before. I'll remember that, though. The next item that I like to talk about is diffraction, but diffraction is a bore. Let me just remind you what diffraction is all about. Suppose you have a circular aperture like a lens, and you have a nice electromagnetic wave coming in. What happens is it will not focus down to an absolutely beautiful zero position point. It'll have a certain finite width, and this width will be surrounded by maxima and minima that looks something like this, the so-called sombrero hat type of function. It has rotational symmetry. It's called the Airy pattern, and when you look at it in a relatively careful way, if you get far out, say about the fourth or fifth ring, these rings are decreasing by about the cube of the angle. Now, diffraction is a nice thing because it is beatable. If you apodize the aperture, that is to say, you get rid of the edge effects by gently turning the edge on, a process known as apodization, you can bring these side lobes down fantastically. If you can't do something like that, you can build a re-imaging section into your telescope, put in a so-called Leo stop. Now, if anybody knows anything about astronomy, you should know what a Leo stop is. It was invented a jillion years ago so that heliographs would work. Get rid of diffraction and scattering from the various, mostly diffraction from the various from the various edges. So you could look at the sun's corona without the aid of an eclipse. And it was done many, many years ago by Bernard Leo. Okay. What happened to my cue cards? There they are. Okay. So I'm not going to tell you any war stories about diffraction. It's just that if you know you're going to have a sensor with good off-axis rejection, you take into account the fact that you're going to have to suppress diffraction, especially if you have a long wavelength instrument, by taking account. Okay, there's only one thing left, and that's mirror scatter. And that's the one that turns out to be the real bugaboo. Now, let's face it, all of us think we know what mirror scatter means. But when you let a quasi-theoretician or a theoretician get a hold of something like this, the first thing they have to do is invent a term that confuses everybody. And indeed, this was done. Instead of talking about mirror scatter, we talk about the so-called BRDF of the mirror. And the BRDF of the mirror is a bidirectional reflectance distribution function. And there is some reason for doing this sort of thing. And you look at it from the following point of view. Take a look at the geometry, of which this is just a crude approximation. Let the incoming and outgoing rays be the blue rays, and let them be located in the YZ plane. And if you have a nice mirror at this point here, then the angle of incidence is equal to the angle of reflection, so that if this beam is characterized by a watts per square centimeter number, you'll have watts per square centimeter coming in, and the same thing will happen on the one going out. You'll have watts per square centimeter going out. You ratio one to the other, and you get the reflectivity. However, if you move off this reflected ray, say out to this one here, what you're looking at is scattered radiation. And the scattered radiation does not have watts per square centimeter as the unit because it's a scattering phenomena. It's a watts per square centimeter per steradian. So you ratio one to the other, you're left over with a per steradian. And those are the units for BRDF. In the early 70s, everybody thought they understood what BRDF is, and they made measurements. Here is the culled results of early BRDF measurements on good mirrors. This is about the 1970s. And they're not the same mirrors, but each contractor that measured, and there were some other government labs also, claimed it was their best mirror, and it was about the best mirror you could get. Well, you can see there's a big difference between this guy and this guy here. You get a feeling, hey, this guy is sloppy and this guy's a liar, but that's neither here nor there. Aerospace did offer to do this sort of thing, and the Air Force guy said, look, you do something like that, the only thing you're going to do is put another curve in here. We don't need that. The solution to this kind of problem is one that has been exercised since time immemorial. What do you do when you have a problem like this? You institute a round robin. And it can provide you with quite a bit of job security. A round robin was constituted in 1977, and it did alleviate this phenomenology just a bit. In fact, quite a bit. however, not perfectly. And I show you an abstract of a paper that was given in 1988 in another round robin. And it measured aluminum mirror, 7 angstrom unit RMS, measured scatter, blah, blah, blah. A factor of 5 on the aluminum mirror. Hey, they're still off by a factor of 5. We've made progress over 13, 14 years, but we're still not there. You read down at the bottom, you can see that people are incompetent, the instrumentation is no good, and so on and so forth. The usual sort of thing. I.e., this round robin is not dead. It goes on. The people have changed, some of them, but it's still good for quite a bit of a job. From time to time, I want to say one other thing here. We'll leave that little for later. I guess I will say it. BRDF measurements are not easy. Suppose you had a mirror that had a BRDF of 10 to the minus 4th per steradian. What you would do is you take a laser beam in and have it come back out. Then you'd move 1 degree off and you put a detector there and measure it. You'd have to make a 10 to the minus 8th measurement if your detector was 10 to the minus 4th steradians. Okay? So to get to the 10 to the minus 4th BRDF with a small detector, you have really got a 1 part in 10 to the 8th type measurement to make. And even that's not very good. A 10 to the minus 4th steradian detector is 10 to the minus 2 by 10 to the minus 2 radians, if it's a square detector. 10 to the minus 2 steradians is 0.6 degrees. You're making a measurement at 1 degree off the reflected with a spread that's 0.3 of a degree on each side with a function that's changing like crazy. You want to do much better than that. So it's not easy. Okay, back to the interesting stuff. From time to time, I'm asked to give, or have been asked to give, sort of tutorials to the Air Force when they bring their new people in. For those of you who don't realize it, the common tour for an Air Force officer is about 3 years. And you just get them broken in and taught a little bit and they're off. And you have to do the same thing for the new guys. So this is sort of a tutorial view graph, and it's entitled BRDF over 5 orders of magnitude. Now, this is BRDF at 1 degree. It'll have a certain fall off, which I'm not going to go into. These comments over here are mine, and I take it from 3 times 10 to the minus 6 up to about 3.3. But let's take this one first. 3 times 10 to the minus 6. I say that this is theoretically possible from the following point of view. The inherent scatter of a mirror is due to its micro roughness. And one can turn cranks with respect to various and sundry type theories, given a micro roughness, which is usually characterized by an RMS roughness and an autocorrelation length. I don't want to go into an autocorrelation length, except to say, if you think of a grating as a mirror, the autocorrelation length for a grating is the groove spacing. Okay? It becomes more random for a mirror. In order to get 3 times 10 to the minus 6 in the infrared, you have to have an RMS roughness of less than 5 angstrom units. Now think about that a little bit. What does a roughness of 5 angstrom units mean when sort of the nickel atom is about 5 angstrom units big? And then you really get to start thinking about these sort of things. Well, classical theory says it's really the free electron, or the sea of free electrons that are doing it. Well, so suppose I have an atom pop up 1 unit. Well, the electron sea has got to do something there. And besides, when you get down to that small dimensions, you really should start thinking quantum mechanically. So I really don't know what that means. Although I see quotes occasionally now, we have got a capability of measuring RMS roughness to 1 angstrom unit with a root mean square deviation of 0.02 angstrom units. If you find out how to explain it to me. Well, I think, okay, it's theoretically possible. Aging is probably a severe problem. If you did this in a smoothing sort of fashion, you subjected the surface at least to quite a bit of heat, and if something goes wrong, you'd have atoms popping in and out, and you could ruin it very easily, I believe. Secondly, and this is the important thing, titanic cleanliness requirement. You see, if you're talking about an RMS roughness of about 5 angstrom units, and you drop a mountain on that plane, say worth about 5 microns, a particle, all bets are off. 3 times 10 to the minus 5th, edge of the state of the art. I know some semi-reputable people who have claimed that they have measured a mirror with this quality. I say semi-reputable because, well, they're pretty good, but they're contractors, okay? Heroic cleanliness requirement. You still got the same sort of thing. Move down a notch. 3 times 10 to the minus 4th. I believe this is well within the state of the art. Only huge cleanliness requirements are to be invoked. I do know really reputable people who have measured mirrors of this type. In fact, I may have even seen one at one time. Unfortunately, it is 3 times 10 to the minus 3 that one usually ends up with. And this is proven long-term performance. Looked at a lot of sensors, a lot of sensors in the infrared, and invariably, when they've shown contamination problems, they've had a BRDF of the mirror that could be explained as 3 times 10 to the minus 3. And people have taken care to try and keep these things clean. So there is a significant cleanliness requirement here. 3 times 10 to the minus 2. Some soot and greasy fingerprints allowed. A little more crudely, or a little more not so crudely, is that it's a sort of mirror you look in the morning. Not so great, but I mean, at least you can recognize yourself, usually. And then finally, 3 times 10 to the minus 1, 0.3. Well, 1 over pi is a characteristic of a so-called Lambertian surface. Lambertian surface scatters equally in every direction. So if you had a Lambertian surface illuminated, it didn't make any difference where you look at it. It has equal brightness. And it turns out that if you conserve energy, it has a BRDF of 0.3. Now I say sandpaper because I'm in the infrared, and believe it or not, there is a paper in the literature that says if you want a good Lambertian surface in the infrared, you get yourself some fine sandpaper and gold coat it. Gold-plated sandpaper. I think that would go over great in Congress. Okay, war story. Now let me say something here. I intimated before that it's not the BRDF, the achievable BRDF of a mirror, that has turned out to be the problem. It's maintaining that BRDF. And maintaining that BRDF, all the circumstantial evidence that you can think of is now in, and some first-hand class experience also indicates that it's contamination, particulate contamination. For cryogenic sensors, where if you let a little water condense out of your mirror, you're in big trouble. The condensable sort of things can hurt too. It is my opinion that people have really not faced up to this problem. And I ran across a quotation from G.K. Chesterton, where his protagonist in this novel proclaims the following statement, and I think it explains it, or it's self-explanatory. It isn't that they can't see the problem. It is that they can't, it isn't that they can't see the problem. It is that they can't see the problem. The solution they can see, the problem they cannot. Okay, to this war story now. In September of 1977, GL launched a probe called SPIRE, Spectral Infrared Experiment. It was a 2 circular variable filters mounted on the back end of a telescope. They launched it at either local sunrise or local sunset, dawn or dusk. It got up there, it could turn one direction and look at an atmosphere that was sun illuminated, turn it 180 degrees and look back and see a nighttime type atmosphere, or right down the center at 90 degrees and see what was called a terminator region. And around a year later, they had this data all analyzed, and we were graced with a visit from 2 geophysical lab people, Dr. D.R. Smith and Dr. A.T. Stair. Some of you may recognize A.T. Stair's name. And they were going to enlighten us about the experiment called the SPIRE measurements. And I hadn't realized it at the time, but I'm only being slightly facetious now. We were subjected to the good cop, bad cop routine. Don Smith was the bad cop, and he got up and sort of accused us that we didn't know what was going on with respect to Earth limb radiation, and to a certain extent, he was correct. He also said we don't know anything about sensor design, and therefore, why are we trying to help the Air Force out and berated the Air Force because they were trusting us. A.T. Sterr got up and said, well, I hope you excuse the youthful enthusiasm of my fellow investigator, but you know those sort of things happen. He said, let me try and put things in correct perspective for you. Here is the data that came out of the Spire sensor. And, you know, Don Smith said exactly the same thing. The daylight scans were the two triangles, and the Terminator and night scans are the dots. And you can see, well, hardly pays to talk about it, but the triangles do lie a little bit higher than the dots, so there's not really a big effect there. This is the result of an AFGL limb model calculation, the so-called DEGS model. And as you can see, for low tangent heights and high radiances, it follows pretty well. We're off a little bit. We would really like to shove that up a little bit. Got the shoulder here, which you don't understand yet, but if you look very closely at the limb model, you see there's sort of a beginning of a shoulder there. We're looking at that to see if we can enhance that phenomenology and maybe hopefully sort of explain this. And shoulders sitting on the side of limb scans like this usually indicate a sort of layered effect in the radians. He said, but you guys, you know, you're really stuck. Up here at high tangent heights, around 230 kilometers, the model differs from the measurements by a factor of 100. Now, if you guys have been using the DEGS model to design your sensors and saying, hey, at about 200 kilometers, I'm expecting a Earth limb radiance of about 10 to the minus 11th, and if you're background limited, and believe me, we were, you're off by a factor of 100. Factor of 100 in the background, if you're background limited situation, means you're off by a factor of 10 in signal to noise. And therefore, your sensor is going to operate 10 times poorer than what you had anticipated. Panic in the streets. I asked the question, however, did you guys take into account the fact that you're looking pretty close to the Earth and you may have to put up with non-rejected Earth radiance, non-rejected Earth shine, call it what you like? I said, yeah, we did that calculation, and it's way down in the mud here. I said, have you got the data? He said, yeah, we made point source rejection measurements. And they gave me a graph of the data, which the point source rejection function versus angle, that was about the size of a postage stamp. And I had to blow it up a bajillion times, but I finally got the OFVR curve off of it and did a calculation. By that time, of course, they were long gone, but here's the result of my calculation. Yeah, you sort of believe what's going on here, but when you get over here, that's damn near a perfect fit. Well, what happens, of course, is that when things like this, the Air Force becomes extremely happy. We got AFGL on one side, we got aerospace on the other side. Let's have a party. So there was a, what did they call it? Interchange meeting. So it was in December in Boston. I make this statement also. I did a lot of traveling on this and other programs. And the places to go to were Boston and Minneapolis, Florida, and Texas, okay? Guess which always happened in the winter, and guess which always happened in the summer. Okay, this was no exception. This was a December 7th or 8th or 9th meeting at AFGL, and we went through the harangue here, and I finally think I convinced them that they made a mistake in their calculation. But it was not a big mistake. It was only about a factor of maybe 5, not a factor of 100. And B, they made an totally unwarranted assumption with respect to the data that they fed in to the calculation. And of course, they didn't like to hear that at all, so we had a big sort of argument, and not argument, debate, okay, interchange. And he said, well, A.T. Sterr was there, of course. He said, well, look, he said, you know, this is the 15 micron region. This is on top of the CO2 band. CO2 is optically thick. You're not really looking at the Earth. You're looking at the top of the CO2 where it becomes optically thick, and it's colder there. I said, yeah, that's probably right, but you see, if you bring it up more, you got an Earth with a bigger radius now than you had before, so the sensor's looking close to your Earth. And I said, I think they're compensating. Well, that went on for quite a long while until we came to the logical conclusion that, hey, why do we look at the emission band? Why not look in the window region? If you may remember, one of the window regions that I pointed out was the 11.3 micron region. This is a circular variable filter. They had a lot of data in the 11.3 micron region. Same story. In fact, you know, given a little leeway, this looks like all non-rejected earthshine. And in fact, I got to give this presentation to a number of Air Force groups because we had to follow these guys around, sort of anti-telling them what they got told with respect to the problem area. And one of them ran into a sharp Air Force captain. That's not an oxymoron. This guy was really sharp, okay? He asked the following question. He said, could you move your curve up, or could AFGL move their data down? And I said, I don't know about AFGL, but I figure there's a few kilometers error in their determination. I said, for me to move my data up would require me to change the parameters a little bit. And I said, and that's probably no difficulty whatsoever. I said, yeah, it does look like you could make this entire thing look like all non-rejected Earth radiance. He then made the following statement. It seems to me we have an optics, namely NRER problem, and not an Earth limb radiance measurement problem. So why are we paying AFGL all this money to make these measurements? I couldn't answer that question, but AFGL came out of it after a while, maybe a couple years it took them, because it was no longer important that you make absolute radiance measurements. What was important is you measure clutter. And in fact, that's what they went into. Now, those two Spire slides are two view graphs out of about 50 that I should have gone into to discuss the history from about 1973, 1974 up to the present time, because that tells all the stories. And you'd be hearing things about BMS, high star, Halo, mini Halo, Teal, Ruby, Scoop, DOT, SIRE, DS Cube, Deep Space Surveillance System, SSDS, and others too numerous to mention. Could have told you about things like, hey, we looked at scattering from individual particles on a mirror and how clever we were. Condensables on a mirror. Leo stops, blue haze, clean rooms, and the inadequacy of MIL standards and so on and so forth. And I would have ended up with a discussion of two ATMs. And there are the authors and the titles of the ATMs, and they're written within the last year. And it has to do with SVS, which is the precursor to Brilliant Eyes, and AFP 675 is Cirrus 1A. And this tells in rather cogent terms, in my opinion, what should or should not be done. And the reason I'm not going to go into it is because, like all the other view graphs and the people that are on this view graph, we're all local prophets and suffer that disadvantage. So what I've decided to do instead is replace those 50 view graphs with 3 view graphs, taken from a presentation 23rd of May, 1989, here at Aerospace. And yes, this is the same D.R. Smith who was the bad cop in the Spire adventure. Why did I pick him out? Well, pick out his presentation. Approximately 12 or 13 years have passed, and maybe more important, he qualifies as an out-of-town prophet. Next slide is the data that he had he considered. The first 7 or first 8 are geophysics sponsored or geophysics run probe shots. This is a contractor one. We've talked about Spire before. ELC is the Earth Limb Clutter Experiment, which some people in this room have worked upon. ZIP 1 and 2 was the zodiacal infrared probe to measure the radiance from the zodiacal dust cloud in the galactic, or what do they know? Ecliptic? Is that what it is? What is it, Ray? Ecliptic. This did not, of course, look very close to the Earth. They weren't interested in looking close to the Earth, but they were interested in looking close to the sun. And the sun's a pretty bright source, so he got data out of that. ELS, that's the sensor that I showed you in the beginning. It actually did fly. Got some data back. Unfortunately, it crashed without aid of parachute. So it was useless. And these other ones here. Well, I'm not going to go through his analysis, but rather just show you his summary slide. And you can read it. Well, the only thing I can say about this is that I'm happy he's joined the fold. And the only thing that I did find a little bit disconcerting was a statement here, the telescope, blah, 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 background at high species-dependent altitude. Well, it turns out what he means by high altitude and what we mean by high altitude are two different things. So there's really no disagreement whatsoever. All the data that I've talked about so far has been about infrared sensors, and invariably the infrared sensors were cryogenically cooled. And even though the condescension was made that yes, indeed, it probably was contamination that did the dirty deed, it may have been condensables that got out on the mirror and therefore ruined everything, and that things like visible light sensors would not have this problem because they're not cryogenically cooled. In 1989, a sensor called VIEW, the Visible Ultraviolet Experiment, was flown on a well-known satellite that reached very high altitudes. Part of the mission plan, part of the program plan for the VIEW sensor was to measure its capabilities, how well it operates against the hard Earth. Consider the VIEW sensor as sitting way out here someplace, looking down at the hard Earth. On December 13th, 1989, they ran the non-rejected Earth radiance experiment. The sensor was positioned so that its line of sight detector field of view was located approximately 10,000 kilometers above the Earth at the North Pole. We were almost at winter solstice, equinox, whatever they call it, and therefore the terminator is tipped almost to maximum. The sensor came down, stopping at 4 places, making measurements. Then the sensor rotated in azimuth 45 degrees and swept up in this direction, again stopping 4 times and making measurements. And so on and so forth, all the way around the Earth. The measurement time was approximately an hour and a half. Unfortunately, no good data was obtained in the dotted region of the graph here. Something went out. Spotty data was obtained at 90 and 135. And this is the data that was obtained in the 45 degrees, 225 degrees case, and 0 degree case. When one looks at the data in a little more detail and puts in the 90 and 135, which points way up about here, there is about a 2 order of magnitude spread in the data as a independent of tangent height, and there's an additional more than 2 order of magnitude spread between the data as you go over a function of tangent height. And the name of the game was explain it. Well, it turns out, of course, because of the nonlinear characteristics and the rather specific orientation situation with respect to sensors of this type, scanning down in this region where you've got a dark cap as the first region closest to the sensor is going to be vastly different than the case when you scan down in this region where the cap and most of the Earth underneath it is illuminated. When you take that into account, and it can be taken into account, and then you take into account also that, hey, there is a spread in this data as a function of tangent height because you're further up than you are here, this more than 4 order of magnitude variation was brought down to a factor of about 6 variation in terms of the explanation. The factor of 6 also included approximately a factor of 2 spread, inherent spread in the data itself, these lines here. The other factor of 3, or 2 or 3, is unexplained at this time and may remain so, although there are possible explanations for it. Now, I said it got explained. It got explained on what basis? What I did was take a general point source rejection function like I illustrated at the beginning of this talk and turn the crank. If it's diffraction, then you know it's got to be beta cubed and fast. And in fact, you can make a calculation as to how much it should be for a visible light sensor. Second order effects are usually very small unless they're the only ones. And essentially that's what it turned out to be. Everything could be blamed on the BRDF of the primary and secondary mirror. This sensor is a center design, and the primary and the secondary sat out in front of the field stop. They both could be illuminated by sunshine. So when you took the both of them together, you could derive a BRDF for that sensor on orbit. Well, in order to make a full story, we'll take a look at a sort of history of the VIEW BRDF. The sensor was built by an outside subcontractor, and when delivered to TRW, the main contractor for this endeavor, they claimed the BRDF of the primary and secondary was 7 times 10 to the minus 3 with a fall off of the 1.8 factor. Now, they had to do a bunch of tests at TRW. One of the last that they made was the so-called point source rejection function measurement, and they came to the conclusion that, boy, things were really bad. And, of course, the second solution for Air Force type problems came up. When you run into a problem like this, you form a Tiger team. And a Tiger team met and pontificated for a while, and they came to the conclusion that it's probably a dirty mirror. And they opened it up, and sure enough, there looked like a bunch of men with their dirty little feet had been running across the mirror. And they made an endeavor to clean it up. There was a lot of particulate contamination. There were also a few sleeks and scratches which you couldn't get off. And they went through a lot of pain and trouble. They built a device that they could get in there and blow the particle off the mirror and have a vacuum cleaner underneath it to catch it. Suck it out, so they wouldn't have it around there anymore. And after doing this sort of thing, they did another point source rejection function measurement, and they said, hey, we're good. Launch. And, of course, they did have a time factor to worry about. They had to button the thing off and send it off to the Cape. Well, this is what we derived on orbit from the measurements. 0.184 beta to the minus 2.4. Talking to the people who were involved in this sort of thing, they said, boy, that's like the performance we had when we were here, not here or here. And you think about the situation, the way they did things, it's probably not too surprising. They cleaned the mirror surface. They did not clean the inside of the telescope barrel, the baffles, and so on and so forth. The people who were doing the cleaning said, hey, we don't have to. It's not dirty. And you say it's not dirty because you can't see it. And, of course, the sensor had to go through the last shake, rattle, and roll test called launch. It is our opinion that the dust got redistributed on orbit or shortly after launch, and you're right back to the same old situation. If you take this BRDF and plug it into the requirements paragraph for the requirements goal performance of the VIEW sensor, you'll find that the VIEW sensor with this type of BRDF failed by a factor of 60. So, if anything, visible light sensors are in no better shape than infrared, and I have a suspicion in some cases they may be even worse. This was recognized in a paper that was given at an SPIE meeting, recommendations for other programs. Contamination control should begin with the design, blah, 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 blah. Should not as us, special tooling. The only true solution, contamination control problem, is to implement a more direct system of monitoring and so on and so forth. And since the two of the authors were from TRW, they also qualify as out-of-town prophets. Now this morning, I got an ATM in the mail from one Gregory Smith, and since he's here, he won't mind if I extract a little bit from it. I give you two items. An extraction out of the Hills Dowling Arnold paper and out of Greg Smith's, and I'll let you read them. Now you tell me who wrote what. Notice, in particular, must have the power to stop everything if there is a problem. Nobody's going to buy this. What I'm saying is, Keith Chesterton said, if nobody's going to buy it, you're never going to have a good sensor. Never. I've reached sort of the end of the line here, but I would like to say a few words concerning. As you can see, I'm not against or I'm not afraid of bringing in really good outside profits. And a few words of concern, of course, are about cleanliness. And that's all, folks. sensors are concerned? Not one that I know of that had a look close to a great source. Not one that I know of, and not one that Dan Smith knows of either.
How many millions is that?
Millions of dollars? Or what? I don't know. Yes, Ray.
This Sears situation did have some interesting history go on just before launch, and I'm sure you're well aware. I've been up to Utah twice now, and I've been unable to get a hold of any of the data from that mission yet to see how much information there was in it. It'd be very interesting to see how much that did before launch helped us recover from
I have a tremendous amount of hope that they really did do something. On the other hand, I have found in this business being a Cassandra is the thing that wins for you every time. You have to be a pessimist. I will make the following statement. As far as Cirrus is concerned, I don't know too much about the interferometer because I didn't look very closely at that, but I looked at the radiometer part. If they show up with a flat level, like I showed for the Spire measurements, a flat level of 5 times 10 to the minus 9 watts per square centimeter, per steradian, per micron, anywhere within their band pass, they did about as good as everybody else. If they show up poorer, they did worse. If they did better, then, hey, they will hold the championship. And the longer you wait, the less hope I have. Oh, I agree. I had to wait a year for the Spire data. Patience is a virtue. Right. Well, if the mirror gets dirty, it stands to reason that the container that it's in, namely the telescope, gets dirty also. And you're never going to get away from launch conditions. So if there are big particles sitting in the container, they're going to get shook loose, and you're just going to redistribute everything. Everything, right. I really hope I've retired by the time people do that sort of thing. That's a whole new thing in itself. I really don't want to talk about it. I'll talk about you on one-to-one, but I don't want to talk about it when somebody's taking my picture and.
has expressed concern that if you do a mirror thing on orbit, you're going to volatilize the material that gear the surface response. They're going to be vaporized, they're going to come out with some velocity or something. And wherever they go, they will then degrade the performance of that surface, whether it's a baffle or another mirror surface. There is no collection device to scoop up all the stuff that's vaporized off of the mirror. And if you change the surface of a baffle to black,
If the baffle is in there to bounce radiation off of.
But it's cold.
Is it shiny? And can the primary mirror see it? Right.
And that's one thing you are helping to reduce.
Talk to me a year from now. I'll tell you what. Melina Hill sat in most of the TR meetings for the contracts that were led by RADC. She could tell you more about it. Sorry, Melina.
Well, there's also
Nate?
Aren't you saying in effect that you need to devise a technology for the telescope as a whole rather than the mirror surface?
Well, let me make a statement that only slightly demeans the on-orbit cleaners. There were a number of contracts let by RADC with respect to, hey, let's see if we can build something to clean mirrors in situ, on orbit. To my knowledge, and I complained somewhat bitterly to the program office about this, my knowledge, there were no contracts let at any time for any amount of money for a contamination prevention situation, i.e., if things get dirty, okay, how do we keep it clean? If we keep it reasonably clean, we won't have to worry about these things on orbit. Not one dime for that, not one dime. And believe me, the Air Force has been asked a number of times by me, indirectly through the program offices. And
I remember the ultraviolet double monochromator at NCAR, beautiful instrument, and they always kept a pressure of nitrogen going through the thing to keep down the keeping it.
you know, that's a sort of prevention sort of thing. People have advocated that sort of thing, and I've heard stories on both sides. And then, in fact, there is a school of people that say, hey, you should keep an overpressure in your instrument so you don't let anything come in. And there are people that say, hey, you should keep an underpressure for other various and other sundry reasons. And to my mind's eye, this problem has not been settled. But it would have been settled in something like a contract that says, hey, here's a sensor. Let's do to this sensor everything we would have done as if we were going to fly it, except that we measure the BRDF of the mirror or some other quantity of the mirror to see what has happened. This has not been done. And, you know, overpressure, underpressures, that's the thing that would fit in to an SOW, statement of work, which I'd be happy to write. Okay, talk about take the Hubble Space Telescope and, for that matter, IRIS. IRIS is probably a more crucial sort of thing. I don't know about the Hubble Space Telescope, and I don't mean to change your question around, but I do know a little bit about IRIS. IRIS never looked at anything even close to a bright source. They did approach the moon once, and for very good reasons. It was a cryogenically cooled telescope, and they had a lifetime problem, and they weren't going to be wasting their time making measurements for a problem area that they didn't worry about. So the only statement that I've ever read in the reports with respect to the IRIS telescope was that, yeah, they got close to the moon one time and everything was okay. Now, with respect to the Hubble, I don't know. Oh, okay.
And when they went close to the surface, or went close to the moon, they did see the signal they expected based on that pattern. So they did not have an ideal mirror to start with, so they don't really know how to get down to the lower levels of the moon. The second thing is that in this search for what goes on with different optically black coatings in spacecraft environments, we found out from a fellow named Mehrdad Bashir up there that there were a number of detections of particular contamination by the IRIS sensor that appear to come from the sensor itself. And they don't know whether it came from inside or outside, so they don't know whether to blame the Martin Marietta flag or inside.
Okay, yeah.
They had to go through and by hand, on an individual case-by-case basis, remove those signals.
Okay. Since you brought it up, it is a problem that I didn't want to discuss because it's not right in line with what I was talking about. But the so-called DOT experiment, designation of optical targets, was a sensor that had a rather peculiar aperture. In fact, it was very asymmetric, and there's sort of two halves of a D. And they saw particles floating out in front of their sensor. There was a rocket launch, so we expect to see some sort of things like that. But they were able to prove conclusively that it was particles because it was out of focus on the focal plane, and they saw the double D structure on the focal plane. And the measurements, they were able to say how big the particle was and how far away it was. And they were able to get its signature beautifully, just like it were a target. So yes, indeed, these problems do exist.